Hi everyone, how's it going? I hope you are having a lovely day. I certainly am. It's a beautiful day here in Australia. The sun is out, it's shining. I wish I could show you how beautiful it is today. Hopefully your day is just as lovely. My name is Professor Andrew Timming, and I want to extend a warm welcome to you for dropping into this lecture series. This is the third lecture corresponding to Chapter 9 of my textbook, Applied Statistics, Business and Management Research. In lectures 1 and 2, parts 1 and 2, I gave an introduction to multiple regression analysis and showed you how it differed from simple regression, which we learned about in chapter 8. In this last part of the lecture series on multiple regression, we will be looking at some of the more advanced concepts associated with this method. Let's not waste any more time and jump right into it, shall we? Just a reminder that this is the textbook that we're using for this lecture series. It's called Applied Statistics, Business and Management Research. I think it's a pretty good textbook, but then again, I would say that, wouldn't I, because I wrote it. But don't take my word for it, read it for yourself. And in particular, I would urge you to read Chapter 9 before listening to the rest of this lecture. Let's jump in. All right. When you're doing multiple regression analysis, bear in mind this means that you have multiple independent variables and a single dependent variable. You might want to keep an eye out for three interesting conditions associated with multiple regression. So the first is redundancy, the second is complementarity, and the third is suppression, also referred to as a suppressor effect. So let's take these one by one so you can get an understanding of what this means. We'll start with the concept of redundancy. What does it mean if you identify redundancy in your multiple regression analysis? Redundancy describes a multiple regression model in which the independent variables predict the dependent variable better individually than they do together. So you probably can come up with a few examples of your own of situations like this, but the one that we went through in the previous lecture in part 2 pertaining to intelligence tests and verbal reasoning tests and numeracy tests, I think gives you a good example of where you might find redundancy. So let's say, for example, you administer two tests, one of which is an IQ test and one of which is a verbal reasoning test, right? And you're trying to use these two tests for purposes of predicting performance. Because intelligence tests incorporate verbal reasoning skills into them, what you have is a situation where the two variables overlap, right? So they kind of predict each other. We referred to this as a form of multicollinearity in the previous lecture. And when your two predictors overlap and predict each other very well, this can introduce complications in a multivariate context. And what you'll find is that if you were to use both of those tests individually in simple regression models, you might find better predictive ability than together. And the reason is that when together, they are redundant. The other concept that you might want to look for is a situation of complementarity. And this describes a situation in which two independent variables predict the dependent variable better together than they do alone. So it's the opposite of redundancy. And again, there's any number of examples I can give of this. The classic one that I like to refer to is if you're trying to predict the behavior of a lawyer, right? Intelligence might be one predictor. You have to be smart to be a lawyer, but also acting skills might be another one. You have to be a good actor. You need to be able to perform for the jury and for the judge. So both of those predictors might predict your outcome, your Y variable, but together they do a better job of predicting because they kind of feed off of each other. So that would be a situation of complementarity. Lastly is suppression, also referred to as a suppressor effect. It is rare, but it's possible. I have seen it before in data analysis. And this is a situation where the relationship between an independent variable and a dependent variable may change or be suppressed with the addition of another independent variable. So the presence of another independent variable could potentially change the relationship between x and y, where, for example, in a bivariate context, x might be positive related to y, but because of the presence of the other variable, we'll call it z, x might be negatively related to y. It does happen, and it's interesting when it does. Now, when you're carrying out a regression analysis, whether it's a simple regression analysis or a multiple regression analysis, you should also check or keep an eye on the concept of homoskedasticity or heteroskedasticity, depending on how you look at it. This is one of the assumptions of regression analysis, to have homoskedasticity characterize the relationship. So what does this mean? Homoskedasticity is a good thing. And what it means is that the residuals, or the error terms that we've described, this is the distance between each individual dot and the line of best fit, are randomly or roughly evenly distributed across that line. So you can see an example of that in the top right graph there. The line is going through and the error terms seem to be evenly distributed across that line. Heteroskedasticity, on the other hand, refers to a situation in which the residuals or the error terms are not randomly distributed, and they often take the shape of something like an ice cream cone or a funnel. And you can see an example of heteroskedasticity in the bottom right of this slide. You can see that at the beginning of the line, they're sort of clustered around, but as you move to the end of the line, there's a greater variance of these error terms. And I think all that you really need to know about this concept is that homoskedasticity is a good thing, heteroskedasticity is a bad thing, and you want to make sure as best as possible that each of your variables are homoskedastically related to your outcome. I mentioned briefly in part 1 of this lecture series, in chapter 9, part 1, that is to say chapter 9, lecture 1, that one of the assumptions of regression analysis, both simple regression and multiple regression, is linearity. So linear regression, which is based on the concept of ordinary least squares, assumes a consistent linear relationship between x and y, right? So if you look at the example of x being hours worked and y equals wages, you would expect a positive relationship there, right? So the more you work, the higher your wages, the higher your income becomes. So you can see it's a sort of consistent positive relationship between those two variables. But what if we account for overtime? Some people get paid time and a half when they breach a certain threshold of their work. And when that happens, you find that the wages or the income increases by a factor of 1.5 because they're being paid time and a half. And what this does is it creates something of a nonlinear relationship between x and y, which multiple regression in and of itself has a difficult time coping with. Now, the types of nonlinear relationships that you can see in the real world can be U-shaped, so as the example in the top right-hand corner. They can also be inverted U-shaped, so you can see an example in the middle figure on the right there. And they can even be S-shaped, so you can see at the bottom right an example of an S-shaped distribution between X and Y. Now, as I said, multiple regression assumes linearity, but there are some interesting tricks you can do to assess potential nonlinear relationships in multiple regression. So one thing you can do is you can square all of your values and insert that squared term into your equation. That will tell you whether or not you have potentially a nonlinear relationship. Or if you expect an S-shaped curve, you can cube all of your values and see if that also improves your model. I've also mentioned a few times throughout this lecture series the concept of a dummy variable. So this is the one exception where we can ignore the assumption of linearity between x and y. And the reason is that it's impossible to have a linear relationship if our x variable only has two categories. So you can use dummy variables in multiple regression analyses. A dummy variable is a two-category nominal independent variable. It must never contain more than two categories. If you insert a nominal multi-category, that is to say three or more category variable in a multiple regression analysis, you'll just get nonsense as a result. So it doesn't make sense. It's not practicable. So when you do have a multi-category variable, what you need to do is take that variable and manually convert it into a series of dummy variables. And I've given an example here on the slide of what you can do. So let's say you have a variable that measures race, and it's coded 1 equals white, 2 equals black, 3 equals East Asian, 4 equals South Asian, 5 equals indigenous, and 6 equals mixed race. So when you have 6 categories, what you need to do is create 5 dummy variables, 5 separate dummy variables, right? If you have 20 categories, then you would need to make 19 dummy variables. And what you want to do is to pick one of those categories as the reference. And what I've done in the example on the slide is chosen white as the reference category, but it could be any one of those. It's just a sort of random choice. So from that one variable with 6 categories, you can create 5 variables as described here. So the first dummy variable would be 1 equals white, 0 equals black. The second would be 1 equals white, 0 equals East Asian. The third would be 1 equals white, 0 equals South Asian. The fourth would be 1 equals white and 0 equals indigenous. And the fifth variable would be 1 equals white and 0 equals mixed race. So by creating a series of dummy variables, you can incorporate multiple category nominal variables into your regression analysis. Okay, so now we're getting into some of the more advanced methods of carrying out a multiple regression. And one of the more advanced techniques is to look for evidence of what we refer to as moderation. So what does that mean? Moderation, or also commonly referred to as a moderating effect. So what happens in the context of multiple regression is that occasionally, not always, but occasionally, some independent variables can have a moderating effect on other independent variables. But in order to find out whether you have this moderating effect, you have to carry out some additional tests in the context of that multiple regression. So to illustrate what I mean by moderation, I've given an example here. You can see it on the bottom right-hand corner of this slide. There are two graphs. And what we're doing here is we're trying to understand the linear relationship between training, say training hours, the number of hours an employee spent in training, and job performance. So in this case, training is our independent variable X and job performance is our dependent variable Y. And you can see in the bottom left in figure A that there is a positive relationship here. As training hours increase, then employee performance also increases. So there appears to be a return on investment. But what if the relationship between training and performance depended on the level of another variable? We'll call it a third variable. And let's use the example now of IQ as that third variable. And we're going to ask ourselves, does IQ have a moderating effect on this relationship? And what this means is that you have to look at different levels of that third variable, right? So you can have high IQ versus low IQ. High IQ we could define as 1 standard deviation above the mean, and low IQ could be defined as 1 standard deviation below the mean. And what you can see in the second figure, in figure B, is what the relationship between training hours and performance looks like when levels of IQ are high and what it looks like when levels of IQ are low. So you can see that this relationship between training hours performance depends on the levels of that third variable IQ. And what you can take away from this graph in the bottom right-hand corner of the slide is that the relationship between training hours and performance is much stronger and steeper for people that have high IQs compared to when people have low IQs, right? So when you have a lower IQ, the relationship is still positive. You can see it slants slightly upwards, but the relationship is significantly more positive and stronger when you're dealing with high IQ individuals. So in order to assess a moderating effect, what you need to do is to take the product of the two variables in question. And you can see the equation at the bottom left-hand corner of this slide. So in this case, if you want to test a moderating effect between x and y, you would say y equals b1 x1 plus b2 x2. So those are our two variables, training hours and IQ, plus b3 times x1 times x2, and then you can add a, your y-intercept. And this will show you whether or not you have a significant moderation effect within your multivariate model. Another advanced form of regression analysis is to look at what we call mediation effects or mediations. And we most frequently do this in the context of path diagrams, so the kind of diagram that you see at the bottom right of your screen. So what does it mean to refer to mediation? Sometimes there is a direct and significant relationship between x and y, and you can see that in the diagram below. Grades is x, happiness is y. So as your grades increase, your happiness increases too. But other times, the effect of x on y is indirect and only seen or partially seen through the presence of another variable, which we'll call z here, or z. And that variable I've conceptualized here as self-esteem. So the logic here is that the higher your grades, the higher your self-esteem, and then the higher your self-esteem, the higher your happiness. So you can see here a mediating role for variable z. There may be a direct relationship between x and y. There may not be a direct relationship between x and y, but there is a significant relationship between x and y through z, right? So you can see the direct relationship between x and y is seen in line C, and the indirect relationship between x and y is seen through lines A plus B. So the effect of x on z is seen in line A. The effect of z on y is seen in line B. And what we want to do to assess or to evaluate the possibility of mediation is to take the product of A times B and then compare that result to C to see which is a stronger pathway towards happiness, right? It's a little bit complicated, but as you experiment with more and more configurations of multivariate models, you'll get a better sense of what it means to have a mediation in your model. All right, let's take a few moments just to review what we've learned here in Chapter 9 across these three lectures, across Part 1, Part 2, and Part 3. As you've learned, multiple regression is an amazingly versatile method, a versatile technique. As I said, it's probably arguably the most commonly used statistical technique in the world. And what it does is it involves the use of multiple independent variables that simultaneously or concomitantly predict a single dependent variable, y. And remember that dependent variable has to be metric and normally distributed, so either ordinal or preferably scale, and that's because multiple regression is a parametric statistical test, so it's predicated on that concept of a normal distribution. One multiple regression model is better than multiple simple regressions. And the reason is that, as we've learned, multiple regression allows us to hold constant the effect of other covariates or other control variables in our model so that we can look at the pure effect of a particular x variable on our y variable. Similar to simple regression and Pearson's R, multiple regression can also be used for prediction and explanation, depending on whether you're using a B coefficient or a beta coefficient, the latter being standardized and the former being unstandardized. But of course, you need to watch out for various problems associated with multiple regression. And these problems include the presence of outliers, including multivariate outliers, multicollinearity, for example, when your independent variables highly predict each other or highly correlated with each other, as well as the problem of heteroskedasticity, which refers to uneven error terms across your line of best fit. And lastly, I would point out you should check for various moderating effects and mediations because they can be quite interesting and shine an important light on your data that otherwise you would not have picked up. Okay, at this stage, I'd like you to press pause if you will, and either individually or in groups go through these 6 questions because answering these questions will help improve your knowledge of multiple regression analysis. Thank you very much for taking the time to listen to these lectures on multiple regression. I look forward to seeing you over at Chapter 10. Take care, everyone.